I'm R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this lecture series, we are going to see the topic Power and Poynting Vector for the unit Time Varying Fields and Maxwell's Equations, and the course is Electromagnetic Fields and Waves. So, Poynting vector and power flow is very important to identify the power flow in electromagnetic wave propagation. So, whenever there is a uniform plane wave, to find the power, it is necessary to develop a theorem for the electromagnetic field, and the theorem is called as Poynting vector or Poynting theorem, and it will be originally postulated in 1884 by an English physicist, John H. Poynting, so that this is called as Poynting theorem, and the vector derived from this equation is called as Poynting vector. And now this Poynting theorem is derived from Maxwell's equations. So one of the Maxwell's equation in terms of magnetic field is curl of magnetic field del cross H is equal to the addition of two current densities. One is conduction current density J and another one is displacement current density dou D by dou T. And now we are taking dot equation of del cross H, the previous expression. We get E of del cross H. We are taking dot equation with respect to electric field. So E dot of del cross H is E dot of J plus E dot of dou D by dou T. And there is an important vector identity. Del dot of E cross H is equal to minus E dot del cross H plus H dot del cross E. And we are applying this vector identity right. Both the left hand sides are equal, so we can equate to both the right hand sides of the previous equations. So we can write H dot del cross E minus del dot E cross H is equal to J dot E plus E dot dou D by dou T. And del cross E is equal to minus dou B by dou T minus H into dou B by dou T minus del dot E cross H is equal to J dot E plus E dot dou D by dou T. And now minus del dot E cross H is equal to, and this term minus H dou B by dou T will go to the right side as J dot E plus epsilon E dou E by dou T plus H is substituted as mu H dou H by dou T, and epsilon E is dot dou E by dou T is epsilon by 2 dou square E by dou T, and this can be written as dou by dou T epsilon E squared by 2. And similarly, the analogous equation mu H dot dou H by dou T is equal to dou by dou T of mu H squared by T, and this minus del dot E cross H can be written as J dot E plus dou by dou T of epsilon E squared by 2 plus mu H squared by 2. And finally, we integrate the entire equation throughout a volume. We get minus of volume integral of del dot E cross H dV is equal to volume integral of J dot E dV plus dou by dou T volume integral of epsilon E squared by 2 plus mu H squared by 2 overall multiplied by the volume integral differential component dV. And applying the divergence theorem in order to obtain the equation, we get the left hand side becomes minus surface integral of E cross H dot ds equal to volume integral of J dot E dV plus dou by dou T of volume integral of epsilon E squared by 2 plus mu H squared by 2 multiplied by dV. So if we assume that there are no sources within the volume, then the first integral on the right hand side is the total but instantaneous ohmic power dissipated within the volume. If sources are present within the volume, then the result of integrating over the volume of the source will be positive. If the power is being delivered to the source, but it will be negative if power is being delivered by the source. And the integral in the second term on the right hand side is total energy stored in the electric and magnetic fields, and the partial derivative with respect to time cos this term is to be the time rate of increase of energy stored within this volume, or it is the instantaneous power going to increase the stored energy within this volume. So the sum of the expressions on the right hand side must therefore be the total power flowing into the volume, and thus the total power flowing out of the volume is integral of closed surface E cross H dot ds. So, and this E cross H is called as Poynting vector, and it is given by P is equal to E cross H, where P is known as Poynting vector, and so this is interpreted as instantaneous power density measured in watts per square meter. So this interpretation is subject to the same philosophical considerations as was the description of del dot E by 2 or B dot H by 2 as the energy densities. And the direction of power indicates the direction of instantaneous power flow. And this Poynting vector, we can say it is the cross product of E cross H. The direction of power flow at any point is normal to E and H vectors, because P is equal to E cross H. And we can write as Ex Ax, Hy Ay is equal to Pz Az. And in case of perfect dielectric, this Ex can be given as ESO cos of omega t minus beta z, and Hy is ESO by eta naught and cos of omega t minus beta z. And Poynting vector Pt is equal to multiplying E cross H, we get E squared SO by eta cos squared omega t minus beta z. So to find the average power density, we have to integrate over one cycle and divide by the period t is equal to 1 by f. So we get P z comma average is equal to 1 by t integral of 0 to t E x naught the whole square by eta cos squared omega t minus beta z dt. And the final equations after integration and substituting the limit, we get P z comma average is equal to 1 by 2 E x naught the whole square by eta omega watts per meter square. And since it is a power density measured by the unit watts per meter square, and it also written as 1 by 2 E x naught squared by eta square watts. And in case of lossy dielectrics, Ex Hs are not in time phase, so we can write Ex as E x naught e power minus alpha z cos omega t minus beta z. Hy is E x naught by eta e power minus alpha z cos of omega t minus beta z minus theta naught. And we can write the Poynting vector as Pz is E cross H. And Pz average is 1 by 2 E x naught squared eta e power minus 2 alpha z cos theta eta. And this term e power minus 2 alpha z indicates the attenuation of power density. And this Pz average we can write 1 by 2 real part of E cross H star watts per meter square. Thank you.